Welcome. In this video I want to talk about someone who should be famous and yet who isn't, and it's an injustice that really should be noted and rectified. That person is Hermann Minkowski. Minkowski, famous in some circles, usually among mathematicians, unfortunately, or unfortunately only, is someone who should be properly regarded as the person who completed Einstein's theory of relativity. Einstein, in 1905, wrote a long paper, which outlined the special theory of relativity for the first time. It was a tour de force. But one could say that he didn't quite finish the task because he didn't give a coherent picture of what space and time were like in the new theory. That task was left to Hermann Minkowski, who only really 2 years later completed special relativity in a way which is not properly understood even today. And that's what I want to come to. So what I want to do is give a brief biography of Hermann Minkowski, and then to say why I think his discovery or his invention of Minkowski space-time, which is what he did invent, why that is misunderstood and why the misunderstanding is significant. Because it's a misunderstanding that runs through elementary physics classes around the world. And that's essentially what I want to say, that people misunderstand relativity theory when they understand it at all, that is, when they're taught it at all, because there is a misunderstanding of what Minkowski said and did. That's what I want to get to. First of all, a brief biography of Minkowski, just so that you know who we're talking about. Well, he was born in 1864 in a part which was a part of Poland at the time, named Alexota. Now this changed hands over the course of time, became part of Lithuania, or is now part of Lithuania. But at the time when Minkowski was born, it was part of the Russian Empire. And that caused Minkowski to be under, or Minkowski's family to be under threat, because there were pogroms in Russia at the time. And those pogroms were directed, of course, against Jews. So Minkowski's family moved, when Minkowski was quite young, to Göttingen, to Königsberg. So Minkowski's family moved to Königsberg, which is in Prussia, in 1872. And that's where mostly Minkowski grew up. So in 1883, while he was in Königsberg and was 2 years off getting his PhD, he was awarded the French Mathematics Prize, which was the Mathematics Prize of the French Academy of the Sciences. That was for his work in quadratic forms, and that's significant, as we'll come to see in a minute. Now, he was very young when he got that prize, only 18 years old, and it caused a controversy because it was normally a prize that went to much older mathematicians. But Minkowski's genius was recognized, and we should take care to note it, because he did this work at the same age at which Galois did his work on group theory, and that achievement by Galois is highly commended, so should also be Minkowski's work on quadratic forms when he was 18. He was a youthful genius. Now, genius marked the family. His brother, Oscar Minkowski, was a biologist and a medical doctor he was his older brother, by the way, he did astounding work on understanding the role of the chemical beta-hydroxybutyrate in solving the problem of diabetes. He was nominated for the Nobel Prize 9 times, and that the discoveries that Oscar Minkowski made were astounding, and he's not appreciated either, rarely ever mentioned, but very significant at the time. Back to Hermann Minkowski. Minkowski was at the University of Königsberg initially, and then, crucially, after he had his PhD, he got work at what is now called the ETH in Zurich. The ETH. Now, the ETH is a sort of university of technology, as it were. It's mostly applied mathematics, where it's mathematics at all. So Minkowski wasn't able to exercise his true genius, in pure mathematics, but was teaching classes more in applied mathematics. And one of his students was Albert Einstein. He taught a number of classes to Einstein, and the classes that he taught were mostly in mechanics, but that was exactly what Einstein was interested in at the time. He wasn't interested in pure mathematics so much. He was interested in applied mathematics, essentially into the kind of mathematics that would apply to physics. So this he got in Minkowski's classes. That was in Minkowski's period in the ETH in Zurich, and it was still in the 19th century, the late 19th century, when this was going on. It was around about 1898, somewhere around there. Minkowski then subsequently moved to Göttingen University, which was chaired by David Hilbert, the very famous mathematician David Hilbert. And when he was at Göttingen, he befriended Hilbert and was one of his closest contacts. Now, this is significant because Hilbert also has a role to play in the story of relativity theory. So, Minkowski was at Göttingen, teaching pure mathematics now, and his work there was on the mathematical theory, or the geometry, what he called the geometry of numbers, which was an application of geometrical theory to number theory. And that's what he mainly worked on. But he had worked on quadratic forms, and he knew them well at the time. So his later work on Einstein's theory does not really come as a surprise. As I said before, Einstein published his theory of special relativity in 1905. He had been working at the patent office in Zurich. He hadn't been able to get any kind of decent academic job. He'd been forced to work in Zurich, but it gave him a lot of time to think. So he wasn't burdened down by some of the things which are required of academics, namely teaching classes that they have little interest in. He was able to give his own ideas sort of free rein, and that he did. And over about 7 years, considering the problems that were extant in physics at the time, left over from the work of Lorentz and from Max Planck, from Poincaré, Einstein in 1905, in a sense, astonished the world with his paper on special relativity. Came out of the blue, and what it argued, which no one had really seen before, is that time did not have a universal character, which had been the previous idea in Lorentz and in others. In fact, everyone really. Einstein showed that you could have a purely, what I'm going to call a purely relative time, that it's relative to a frame of reference. And that frame of reference would determine, your velocity would determine a frame of reference, which is your rest frame. And in that rest frame, you would have, as it were, a clock that was attached to it. And that clock would mark the passing of time in your reference frame. But if you moved to a different reference frame, you would have a different time with different durations in that, along that, as it were, in that reference frame. So if you had a reference frame, for example, in which, so you have one which is at rest, and then you have another which, compared to the first, is going at 50 miles an hour, then the clock that is measuring time in the reference frame, which is going 50 miles an hour compared to the first, which is at rest, that clock will measure differently to the rest frame clock. You will have a relativity of time compared to these frames. That's Einstein's great idea, and it's what took most of that long paper, it was 36 pages roughly, to spell out and to show all of the powerful consequences of that view. Einstein also sort of took as a principle that the speed of light would be a constant in every reference frame. So take the two frames as we had before, one which is at rest and the other one which, compared to that frame which is at rest, the one that is going 50 miles an hour compared to the first. In both frames, despite the fact that one frame is going 50 miles an hour compared to the first, the speed of light would be measured exactly the same in both frames. It's a revolutionary idea, extraordinary idea. You've doubtless heard of it. You've doubtless heard this idea, and it comes from that 1905 paper of Einstein. Now, what Einstein did not do in that paper was even attempt to unify the concepts of space and time into one entity. That was left to Minkowski about 3 years later, maybe 2.5 strictly, because Einstein's paper was published in September of 1905. We are 1 year off. It's 120th anniversary. So we're coming close to the anniversary of that event. So Minkowski took what Einstein had done and immediately saw how it could be made into a genuine mathematical theory, a mathematical structure which was already known to a large extent. Einstein didn't know it because Einstein did not, at that point, have very much acquaintance with pure mathematics. So he was limited in many ways. But of course, Minkowski did, and he knew geometry well, and he was able to. Now, what then was Minkowski space-time? Well, actually, no. Before I say that, I should actually point out, I suppose it's one of the most important things about Minkowski's life, is that Minkowski died after he gave a talk on his theory in 1908. He had the misfortune to die a year later. He was only 44 years old at that point, so he was really quite young. He died of an appendicitis in 1909. I think it was the 12th of January. So 12th of January 1909, he died, and that is only 3.5 years after the publication of Einstein's theory. So he managed miraculously to get in this talk in 1908, but it was touch and go. He could easily have died, as it were, before he managed to do this extraordinary thing. And it was a tragedy that he died, because had he gone on, his other discoveries would have shown that he was also an extraordinary contributor to quantum mechanics, which was not born until 1925. And we are 1 year off the anniversary, the 100-year centenary of that event. So quantum mechanics comes in 1925, but what Minkowski had done before he died, the work that he had done prior to his death, also anticipates and forms the background theory to an important part of quantum mechanics. Now, this is going to be a two-part talk. I'm going to talk about the quantum mechanical aspect of this later. Today, I'm only going to talk about the relativity theory consequences of the 1908 talk that Minkowski gave in Berlin in, as I say, 1908. So, what was Minkowski's idea? Well, to understand it, we need to have a picture of it, because it's a geometrical idea. So I want to show you a common picture that runs through Minkowski's space-time. I want to present it to you, and then I want to comment critically on it. So I want to say some negative things about it, but you may recognize this. It's from Wikipedia, so you may recognize it from there, but it's reproduced in almost every class, physics class, on relativity theory. And it's, as I said before, right, it's something I want to criticize. So here is that diagram from Minkowski, or indirectly from Minkowski, from how Minkowski is today presented. And you'll see it consists of two cones. The two cones are called the future light cone and the past light cone. This makes Minkowski's discovery part of what is called hyperbolic geometry. Now, hyperbolic geometry was known before Minkowski, so he was able to take hyperbolic geometry and understand that it gave the best graphical reproduction of Einstein's theory. It was already invented. Minkowski had to interpret it in the context of Einstein's theory, and that was the brilliant contribution that Minkowski made to Einstein's ideas. Now, so we've got a future light cone and a past light cone. What on earth is that? What does that mean? Well, it means this. So call the point at which these two cones meet. Let's call it 0 or O. It's the origin, or you could say it's where the observer is sitting. So you now, where you are now, there is at that point, at every point in every moment of time in which you're sitting there, there is, you as the observer are following a line, and at every point on that line, because you're at rest, as it were, in your reference frame, there is these two cones. If you were to flash a torch from where you are, then the rays of the torch would be transmitted along the future light cone and spread out from there. Now, the future light cone it's a conic, that it has a surface that's two-dimensional. It's a surface of two dimensions. I want you to try to imagine that forward cone is actually 3 dimensions. It's a 3-dimensional cone. So it's not a surface so much as it is a volume. In other words, when you flash the torch, the light from the torch goes along a 3-dimensional cone, the rays going along along that cone into your future. Similarly, where you are, the origin, you're the observer, O, all of the light that you are now seeing, comes to you at the point at which you are as a 3-dimensional volume of light. Look around you right now. Look around where you are. You are seeing a volume of light coming to you. That is your past light cone. Now, this structure, this light cone structure, is not just at one point, it's at every point in a space. So there's a 4-dimensional space, and it is filled at every point with these cones. These cones determine, because of the absolute, the nature of light as a constant, that cone is going to be everything that the limit of everything which you can affect towards the future. It will be, and you, where you are, is everything that is affecting you in the present, that is coming to you at that present. If it's coming to you as light, it's coming along the surface of that past light cone. So the light cone structure, this 3-dimensional thing, which we can only represent with 2 dimensions, but the 3-dimensional existence of this light, these 2 sheaths of the light cone, this gives you what you can affect in terms of light, where the light will go if you emit light from a source where you are. And it also is the convergence of all the light which is converging on the point at which you are at from the past light cone. And that, if you look around, that is what you are seeing. You are seeing the past light cone. It's all that you see is coming to you as light along that past light cone. I'll call it a sheath, but you have to remember that it's 3-dimensional. It's a 3-dimensional surface in a 4-dimensional space. Now that light is taking time to get to you in your reference frame. It takes some time. I'll come back to the real meaning of that in a minute. But light takes some time to get to you from other objects which are far away. For example, the sun. It takes more than 8 minutes for the light to get from the sun to you now. So, you probably know this. So, you're seeing the sun. It's out there, believe me. I'm not going to look at it, but it's there. That sun is 8 minutes away as you're seeing it. It's 8 minutes old. It could have exploded by now. If it had exploded, it's going to take 8 minutes for us to find that out. The stars are even further away, as you know. So light years measure the distance, for example, of stars to us now. For example, I think the nearest star is something like 4.6 light years away. It's the roughly where in Alpha Centauri is. And Alpha Centauri is the horrible, hopeless destination for the family Robinson in Lost in Space. That's where they were going, 4.6 light years away to the nearest star. So it takes 4.6 years for the light from Alpha Centauri to get to us, and that's the nearest star to us other than the Sun. As you go further out, it takes even longer for the light to get to us. Looking out into other galaxies, you're looking way into the past. And astronomers can look very far into the past now with their telescopes. They can look billions of years into the past. In other words, that the light from those galaxies is taking billions of years to get to us now. So your moment now when you're sitting here, the light that comes to you is 8 minutes old from the Sun, and it's billions of years old were you to be sitting here at night and the stars outside were to be shining their light on that light cone, your light cone, to now. So, your now, what you take to be now, what you take as you look out onto the world, is old. In your reference frame, it's old. And that oldness is an important factor about it. It means that because nothing travels faster than light, it means that you have no experience whatsoever of anything which is outside of that light cone. What is, for example, what is outside your past light cone? Whatever that is, whatever's happening there, it's not something you can experience. So, it also follows that in the forward light cone, what you are able to affect cannot go faster than the speed of light. And so what is outside of that future light cone is nothing that you can influence. Now, in a purely mathematical way, you can define something which is called, rather misleadingly, space-like intervals and space-like vectors. This entire cone structure, by the way, is a cone of vectors. Future light cone gives you vectors that point within the cone, and what are called time-like vectors are given to you inside that cone. They travel slower than the speed of light. So suppose someone, throws a piece of paper and hits me. That is going slower than the speed of light. It's traveling along a time-like curve. And its speed within my frame of reference is able to be measured along in my reference frame. The same, so that's in the past light cone. Everything that happens when the paper is thrown at me, it hits me, it's traveling within the past light cone to me in my now. And at the same moment in my now, I am getting all of the light from that past light in my past light cone. It is converging on that moment where I am, that now. So the time-like, the past, it has two components. It has a light-like component, which is given by the surface of that past cone, and what I can influence at slower than the speed of light is given by the forward cone. The internal parts of the forward cone are given by vectors inside that sheath, that three-dimensional sheath. So you've got, in a sense, 4 dimensions. You've got a 3-dimensional sheath of the cone, and you've got an internal part, which is, as it were, inside that cone, which are the time-like vectors which I can influence. So what is now? What is my now? Well, I've already given the hint of it. It's everything that can reach the observer point O in the diagram. It's every vector that can reach me in that, or every line that can reach me inside that cone and on the surface of that cone. Everything outside of that cannot have any influence on me. You could say, I don't know of it. Now, Minkowski didn't just use this diagram. This diagram comes, by the way, I should, for credit purposes, say it's due to K. Ames-Quatsi, who put this diagram in multiple places onto Wikipedia. Credit to him. Now, what I want to say, even though this is completely in the way that physicists talk about this, what I want to say about it is it's slightly wrong. Because if we understand what the now is, it is restricted to the inside of my past light cone and the sheath of that light cone, which is on which light travels. Now, that is my present moment. And it's personal to me now. It's personal to you now. Where you are at that moment of time that you are now listening to this, that is your past and your time-like past and your light-like past is unique to you. Suppose someone were, say, 16 feet away from you, they would have their own cone going through them then at that point. Now, the speed of light will be the same for both of you, but you may have different temporal things happening to you. You have a different temporal past and a different light-like past. The person 16 feet to you doesn't have exactly the same visual experience either. The light cone in the past may be blocked so that they can't see Alpha Centauri at this moment. Maybe it's, maybe it's blocked by a wall or something. Maybe a cloud. They can't see it because of a cloud. You can see it. Now, to understand this, we have to look at what Minkowski's real contribution was on this. Namely, that what Minkowski did was he changed what we call the metric for the space. So if we take a four-dimensional Euclidean space, which is not, by the way, something which we have an experience of either. It's take the geometrical construction of a four-dimensional Euclidean space. Now, what Minkowski did was change what we call the signature and what he called the signature of the metric. He loosened the idea of the metric so that it's of this form. This gives you a quadratic form for the metric, which comes from the metric, and the signature of that quadratic form is the number of negative and the number of positive signs. Negative signs, plus signs. And you notice that that correlates with the metric because we have one positive sign and three negative signs. The negative is on time. So the temporal aspect of this metric gives you a positive interval as you go over time, as you're measuring by a clock. Your clock, if you look at it in your experience, you have a positive readout for the clock as it gives you the time 1 o'clock to 2 o'clock, 3 o'clock to 4 o'clock, etc. So the metric gives you a positive value for temporal intervals. If you look at the spatial interviews, X, Y, and Z, there's a negative sign in front of them, each of them. That means that the metric gives you a negative value for everything that occurs outside of your light cone. Everything that is outside of your light cone, what is called in that previous picture space, is not something, this is my major point, it's not something you're ever able to experience. You can only experience things that are within your light cone. So when we talk about space, Minkowski didn't use that expression. He talked about space-like vectors, space-like intervals. And these, in the metric that he was using, which is the one I've just given you, that space-like interval is negative distance. What on earth is a negative distance, you say? What on earth can that mean? Well, he chose it in this way because we don't have any experience of that. We don't have any experience of what a negative interval would be because we don't have any experience of what is outside of our light cone, so it doesn't matter. Now, you may say, well, surely we have some experience of space. Do we? We don't have any experience of the space-like areas outside the light cones. What are we experiencing then? Well, suppose I'm measuring my current room. What I'm doing is I lay a tape measure along a wall and I read it off. Laying a tape measure and reading it off is an activity that requires me to do something in time. Even if I were to measure the distance using which is currently done, using rays of light, I fire a ray of light at the far wall and I get a readout from that. Fine. That's still not outside my light cone. That's doing something within it. As I move upwards in time, the activities that I do to measure the room are time-like or light-like activities. Now I'll get a reading from that of X, Y, and Z, which are measurements of the room. I'll get a measurement of the floor size and I'll get a measurement of the height. Great. I haven't gone outside my light cone for this because you can't. There is no way of doing that. So when we have in this diagram, to go back to it, when we have in this diagram hypersurface of the present, space being mapped out on this surface, you can define it. No question, you can define that using the idea of orthogonality within your frame. You can define a present, but it's not a present that you see. It has no definite experiential contact. And that present that it marks out on that diagram, if you were to change your velocity, that present would be different. But who cares? Because even if the present is different, you don't have any experience of either of them. You see, I'm excited by this because this causes untold confusion in students. They think the hypersurface of the present is what they are seeing when they look around their room, what they are seeing when they look out onto the world. They are not. You are not. We are not ever able to view that hypersurface that is located outside of the light cones. It's a purely abstract, non-experiential, certainly definable by orthogonality, and Einstein, by the way, did define it, called the plane of simultaneity, But that's similar to what that is not your now, can't be, and is never. So what Minkowski did, using the picture of the light cone, was able to be much clearer about what you could experience and what you didn't, and what the structure of that. He invented that. That is not strictly due to Einstein. You could say that Einstein was still marginally confused about this matter in the way that he thought this went. And many people have been confused about that to this day, because it is very, very common, as in this diagram, which is everywhere in physics instructions, misleads everyone into thinking that that hypersurface constitutes their now. And in an experiential sense, that is not possible. Even in a non-experiential sense, that now, the hyper plane of O, that hyperplane is entirely restricted to a particular vector, a temporal vector, which is at rest. And again, the temporal vector has a significance. The hyperplane that's orthogonal to it has none. Note, however, that in Minkowski's own paper, which was published just after his death, but nevertheless, in Minkowski's own paper, which represented his version of his own theory, you do have a space-like vector. Now, you can look at it here. You do have a space-like vector that is marked, but there is no space-like surface, a hypersurface, because it's irrelevant. There are space-like vectors. They have no experiential significance. Minkowski does not draw in these misleading hypersurface of the present, because it's a complete misunderstanding. You may say, well, maybe Minkowski was getting it wrong and everyone else has been getting it right. No. Roger Penrose, is one of the best expositors of Minkowski. I would say he's one of the few people who really understands Minkowski space-time. And he's one of the few people who've understood it to the extent of being able to extend the idea of Minkowski space-time. So, for example, in this book, which was published, I think, in 1986, somewhere around there, in this book, Penrose and Rindler described Minkowski space-time very close to the way that Minkowski defined it, with much more mathematical detail than Minkowski used, because he was giving a public lecture, Minkowski. And it's really the best account of what Minkowski space-time is. And Penrose and Rindler used the same signature that Minkowski used. And in talking about Minkowski space-time, they pretty much leave out the hypersurface that the Wikipedia diagram puts in, because it's irrelevant. By the way, if you want a readable version of this, because perhaps this version is less readable, then I recommend this doorstop of a tome, The Road to Reality, which is another book by Penrose, his more recent book, or a more recent book, I should say, called The Road to Reality, A Complete Guide to the Laws of the Universe. There is in that book also a very good account of Minkowski's space-time without so much of the mathematical formalism, but enough so that you can get the concept very well. So it's also a very good source for this. So Penrose added to the theory and understood it superbly well. I'm not so sure that in the world of physics, as opposed to the world of mathematics, it has been understood well. And anyway, that's my controversial point. I don't think many people read Minkowski's paper, and I don't think enough people read of the elaboration of it in Penrose, but they should, because it is clear-headed, very clear-headed in a way which many physics discussions are not. Now, Einstein noted in his own account in 1905 that his theory gives rise, the relativity of time gives rise to what he thought of as a sort of a seeming paradox, by which he meant only that it seems to rub against our intuitions. And it's called the twin paradox. That is, suppose you have two twins. They start off, they have identical clocks. So they're together, as it were. One stays at a constant speed with its clock, with his clock, her clock, whatever. The other one takes off in a rocket and goes very fast and comes way back into, and then slows down, comes back into synchrony with the first twin. What happens to their clocks? Well, the twin who has gone at a speed relative to the first and then come back relative to the first, so that they're now, as it were, back together on Earth. The twin who moves with respect to the first one who is still in that frame, that is not moving in that frame. The twin that has moved has not aged as long, not aged as much, because their clock has run slower than their twin's clock. Their clock has run slower than their twin's clock. Einstein thought of that as a sort of paradox, in the sense only that it seems to challenge our intuitions. We now know that that is exactly correct, that a clock that is in motion with respect to another clock will run more slowly. It's been experimentally tested and confirmed. Now, some lecturers I've seen and heard think that this is a paradox, in some sense, as a contradiction. It isn't a contradiction. There is no contradiction, because it's not the case that the twin who stays at home in an inertial frame that's motionless, it's not the case that that twin ages slower than with respect to the first one. It's the twin who is taking off and then coming back into the reference frame of the first one who is aging less. Their clock has run slower. Their heart has beat slower, because your heart is a clock. It's not a paradox in any kind of strict sense. And I'm flabbergasted by the number of people who think that it is. If it were a contradiction, then relativity theory would be false. But it's not a contradiction. It's something which challenges our intuitions, and our intuitions are wrong. It's been measured, and the clock that is in motion with respect to another clock at rest, where they come back into the same reference frame at rest, the clock that has moved has aged, measures less on its clock. So the twin that goes onto the journey and comes back may come back, say, aged a year, 2 years, 3 years, and comes back to their twin who is aged 40 years or 50 years. The clock that stayed with the twin that doesn't move measures more than the twin that has taken off and come back. It's not a paradox. It's a consequence of the special theory of relativity. So much about relativity theory is gotten wrong, including this, which is a fundamental point, that I have been waiting several years to make this video to set this matter right. If you want to understand the twin paradox, you have to look at the time intervals with respect to the Minkowski metric. What happens in a line that runs straight as we've been given it on the Minkowski metric, which was, remember, it's here. What happens? Well, the longest line on that metric is given by the twin who stays at home. And oddly enough, the one that goes off, accelerates off into space and then comes back into the reference frame of the first one to compare clocks, that line is shorter on the metric than the first line. The first line is longer by the clock. It looks shorter on the diagram, but that's just because we're not using the correct metric when we draw the diagram. What looks like the longer curve is actually shorter by the metric. That is the key to the twin paradox. Now, I said I'd come back to this point. What about the metric on the light cone? What is being measured along the light cone? Well, it's the intervals of light. But if you look at the metric, that happens, what light is traveling along is a zero metric. What does that mean? It means that along the light cone, every interval along the light cone is zero. This is zero, this is zero, this is zero, this is zero. All along the light cone is zero. The light, if you want to represent it to yourself, the light is not moving in an absolute sense in the Minkowski space-time. Or you could say, and it is said, I think Penrose puts it this way, the light is eternal. There is no metric for it. It's zero. There is no positive or negative metric for it. It's zero. It's always zero. The light is eternal. It doesn't age. There is no time within the Minkowski metric. There is no time for the light. There is no time for the light. Time only exists inside the light cone as time-like lines, time-like vectors. Out on the surface of the light cone, all of the light that is reaching you, in a sense, is eternal. And if there were no matter, because I mean positive mass, matter, if there were no positive mass in the universe, there would be no time. Time only exists, as it were, relative to it being enclosed by the light cone. Were there no positive mass, there would be no time. The matter that has zero mass has no age. There is no time for it. It exists on its own surface immortally, if you like. Although that suggests measurement in time. And eternal, it suggests a measurement in time. I don't think we quite have a word for what is on the light cone, but every point on the light cone is of a zero interval. So this interval is zero, so is half of it. They're both zero. Minkowski space-time is fascinating, interesting. It's how our universe works. It is frankly astonishing how little it's understood, but it's the key to relativity theory. It's what Einstein missed out on by not having enough maths in order to complete his theory. He did an astonishing job in what he did, but he could not do what Minkowski did. And he needed it he needed Minkowski space-time, he needed to generalize it in order to get his theory of general relativity, which is where you include gravity. But he did not have it initially. He did not have it until Minkowski invented Minkowski space-time. So, what we have then is a theory which is astonishing. It's the beginning of really everything. The two papers by Minkowski and Einstein, this is monumental work. The two of them together, only 3 years apart, monumental work. And we don't pay any real attention to it. I've said this before, I'll say it again. I find it kind of disgusting that Doctor Who, which is all about time and relative dimensions in space, blah, 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 in all of its history, it has not once mentioned the name Minkowski. Not once. It is based entirely on Minkowski's contribution, and it does not mention him at all. All of the people that could have been induced to look up Minkowski, to find out about him, haven't. Because in the popular media, in the popular world, there simply is no recognition of Minkowski's contribution, unfortunately. But it is phenomenal. And Minkowski, as a mathematician, as an intellect, is one of the greatest who ever lived. He was a stellar mathematician, not in any way running Einstein down, because he was astonishing as well. He was a thorough genius. But he did not do pure maths. And I think that if he had, he would have come up with the general theory of relativity far earlier than he did. It took him 10 years to come up with it because he had to learn the maths in the meantime. So there we have it. Minkowski is an utter genius. And Minkowski and Einstein together shaped the modern world. The really significant aspects of what they did. There is no saying that there's anything other than earth-shattering. And they both have to be credited. They both did these things. They were both astonishing. And in the next part of this, as I said, it's a two-part video. In the next part of this, I'll talk about Minkowski's contributions to quantum mechanics. And it also was thoroughly profound and paved the way for quantum theory, which, as I say, was inaugurated in 1925, which is 100 years ago next year. Okay, so until the next lecture, I hope to see you then. I hope you come back to understand what Minkowski's extraordinary contribution was, because that's not mentioned really, I think, at all. I've never seen it talked about, except when I've talked about it. So I feel as though I'm on a crusade to get Minkowski well understood by people who simply don't understand what he did. And so if I seem overly passionate about this and concerned that we should understand this, well, just understand that what I want is for us to pay tribute to someone who created our understanding of the modern world almost more than anyone else. With that in mind, hope to see you next time. Farewell.